Again, I'll be talking about the work that I've been doing with the EPA over the past 4 years. I'm with the ORISE, the Oak Ridge Institute for Science and Education. It's a great fellowship program for students coming out of their PhDs to work with the federal agency, ORISE, as well as the Research Associates program, which is run out of the National Research Council. Both are good programs for students to work with fed agencies. So again, today I'll be talking about the work on nitrogen and I'm going to start off very broadly. I know many of you probably know about the nitrogen cycle, but for those who may not be familiar, I'm going to give a very brief overview of the nitrogen cycle. I think many of you know that most of our atmosphere is actually composed of nitrogen gas. It's an inert gas, largely unavailable for biological use. And because of that, historically, it's been a limiting nutrient for plant productivity and biological productivity. Now, there are a few processes, for example, that can actually convert this nitrogen gas into reactive forms or biologically available forms of nitrogen. For example, lightning can supply enough energy to break the bond to form reactive nitrogen, as well as specialized microbes that can, laser pointer here. So also specialized microbes that have the capacity to fix nitrogen as well. Historically, these are the dominant pathways by which nitrogen entered ecosystems. There was also a pathway called denitrification, which is another microbial process that converts reactive nitrogen back into gas, creating the nitrogen cycle. And again, historically, prior to about 1900 or so, we think that the nitrogen cycle was largely in balance. That is, the nitrogen that was converted to reactive forms or fixed into reactive forms was largely balanced by the amount of nitrogen being converted back to nitrogen gas. And again, for the past century, we've greatly modified the nitrogen cycle. And I want to go through and illustrate what I mean by showing a time course of nitrogen inputs to the U.S. And I'm also going to refer to as nitrogen as a term that I'm kind of coming to in terms of our obesity problem. We need nitrogen. It's clearly a large part of our food, but we do have too much of it, as I'll show in this next graph. In terms of the inputs of nitrogen from anthropogenic sources to the U.S. landscape, we have too much of it that can ultimately cause a number of health and ultimately environmental effects. So it's that fine balance. We need enough of it, but when we have too much of it, it causes a number of problems. The inputs of nitrogen to the U.S. and worldwide have been from anthropogenic sources have come from the creation of synthetic fertilizers, increased cultivation of legumes, as well as a byproduct of fossil fuel combustion, which also convert nitrogen gas into reactive forms of nitrogen. So currently in the U.S., and I'll go into this in more detail in the analysis that I'm going to be presenting, we've increased inputs to the U.S. probably around current, in terms of the background levels that are currently coming in, we're probably about 7 or 8 times higher than what we think are coming in naturally. And actually, it's compared to what was coming in pre-European, it's like 3 or 4-fold because we've done a lot of land conversion that's affected the landscapes and the capacity of the landscapes to fix nitrogen. So again, we have these huge inputs that are referred to as the obesity problem. And some of the problems that come out of having too much nitrogen in the environment is, although, okay, so 50% of the nitrogen in your body on average comes from synthetic fertilizers. Otherwise, half the world's population would not be alive without the fertilizers that we create through the process of Haber-Bosch. But because when it's used inefficiently, when nitrogen is used inefficiently or enters the environment unintentionally, it can also cause things such as harmful algal blooms, the increased productivity of algal species that can produce toxins and harm wildlife and human health. It can cause things known as hypoxia. I think many of you are aware of the hypoxia in the Gulf of Mexico, which is low oxygen water following phytoplankton crashes. That can lead to fish kills, declines in fisheries production. High levels of nitrate, a form of nitrogen that leach into groundwater, can have impacts on human health by leading to things such as blue baby syndrome and possibly linked also to some forms of cancer, colon cancer, and epigastric cancers. And nitrogen that enters the air can also have effects on acid deposition, as well as long-term productivity of forests. So the work that I'm going to be describing today is a synthesis effort that I've been a part of in the past 4 years at the EPA, where we've been using the framework of ecosystem services to link together data that we've collected on nitrogen inputs the inputs of that nitrogen to the landscape, and then also translating those inputs into ecosystem services. I'll refer to those as both final and intermediate services. Final ecosystem services are things like clean water or real products, fish, even agricultural commodities. Intermediate services would be things such as nutrient cycling or provisioning of water resources. So there's different classes of ecosystem services. But we've developed a framework at the EPA that we can try to take some of this information on actually fluxes of nitrogen in the environment and convert them into, ultimately we're going to try to do dollar amounts, put some dollar value on that. And so I'll work through these different steps, these three parts of this ecosystem services approach, beginning with our effort to compile data describing inputs of nitrogen to the US, both natural and anthropogenic sources. And our approach has been to do a kind of a broad scale meta-analysis where we've collected as much data as we can possibly find, looking both at national level and spatially explicit data on nitrogen sources from both new nitrogen, which is nitrogen that's directly fixed from the atmosphere into things like fertilizer or fixed by legumes, fixed by fossil fuel combustion, or natural sources such as lightning fixation and biological nitrogen fixation. As well as recycled nitrogen, which is essentially waste byproducts, livestock manure, wastewater from sewage, as well as deposition of ammonia that gets volatilized off of fields and also from CAFOs and feedlots. We also collected data to look at both export and imported nitrogen, trying to get a net flux, an idea of the net flux of nitrogen in and out. This is to the United States in general, the United States specifically. So we've compiled these data sources. We've compiled in the order of close to 60 individual data sources that describe some aspect of nitrogen inputs in the US. And what I'm going to go through next is kind of the results of that analysis. Starting at the national scale, we put out a paper last year in Frontiers in Ecology and the Environment that summarizes a lot of this work. People are interested in that. I can forward a copy on to Amy or to the group if they're interested in this. And this is one of the main figures from this paper. And so, again, there's 54 total data sets described here. But we've broken it down by whether sources are natural or background inputs. Contemporary non-cultivated biological fixation, that is the inputs that are coming in currently from background sources. Lighting fixation is actually a very small part of it. But you can clearly see, and we've known this for a while, it's good to put numbers, a few more numbers on this, that fertilizer is the largest source of nitrogen to the United States. Second in line is agricultural biological nitrogen fixation or cultivated biological nitrogen fixation, which is, again, N fixation by legumes. You also have a lot of nitrogen that's fixed for industrial products, things such as nylon, plastics, and TNT and things like that for explosives. Deposition of nitrogen, although a main focus of a lot of the efforts for management in the US, is actually is fourth on the list in terms of new inputs. And that's actually because we've seen a pretty drastic decline in the deposition of NOx or NOx compounds over the past 20 years due to amendments to the Clean Air Act. Recycled nitrogen deposition, which is essentially mostly ammonia, makes up the largest fraction we think of recycled nitrogen input. And this then followed by manure applications from confined feedlots to agricultural lands as fertilizer specifically. This doesn't include all manure that's produced, but just the fraction that applies to agricultural lands. Wastewater is actually a very small, is one of the smaller sources, the smallest overall source. And that makes sense as you're losing nitrogen along the production chain. So you actually only see around a teragram of nitrogen entering wastewater, we think, across the US. And then finally, we're a net exporter of nitrogen. The US, we export overall the balance, we export overseas. Now, the bars described here, so the bars themselves are, because a lot of these data sets are interrelated and have common ultimate data set, ultimate sources, it was very difficult to try to come up with some appropriate statistics to do on it. So doing straight means and standard deviations wasn't appropriate because of the non-independence of data. So we used our best professional judgment based on available metadata to pick out what we thought was the best available estimate of nitrogen input to the US in the current period. This is around the year 2000 or so. The whiskers or the error bars here represent the range of all estimates that have been made for those sources. So, for example, we think we have a pretty good handle again on fertilizer inputs to the U.S., and that's because it's tracked pretty well across the U.S. Whereas something like agricultural infixation, although we have data on legume production and legume planted areas, we don't directly measure or track infixation by legumes. So you have a wide range of estimates that have been generated for current inputs of nitrogen to the U.S. Same goes with infixation in non-cultivated ecosystems. There's limited data, limited models, with many data and many different approaches that have generated a wide range of estimates. And you can go through and kind of and rank the level of uncertainty based on those range of estimates. And so this gives us a handle of what we know very well about nitrogen inputs to the U.S. and what we don't know very well about nitrogen inputs to the U.S. And so again, we know fertilizer, we know things such as industrial products, we know deposition, we know all these things that are tracked either economically or through regulatory means. But we don't know as much about things such as that are not tracked as well or measured as well, like infixation in particular. We've also been able, and so I was going to show this time course again, just to show again how the time course of nitrogen inputs to the U.S. have evolved over the past century. So again, with the development of Haber-Bosch process, the process that really creates fertilizers in 1913, just celebrated the centennial of it actually. We really saw it take off in fertilizer use in the U.S. right around World War II, post-World War II. And the use of fertilizers have increased quite rapidly up to about the late 1970s, 1980s. We've actually kind of plateaued out in terms of the amount of fertilizer we're applying to the landscape due to increases in nutrient use efficiencies by development of different strains, developments of different practices in agricultural lands. It's actually pointed out that although you may think that this is a large amount of nitrogen being applied to the U.S. landscape, without advances in cultivars and techniques that were developed back in the 60s, 70s, and 80s, we actually might be seeing 20 or 30 more teragrams of nitrogen coming into the U.S. landscape. So we actually have seen some improvement in our nutrient use efficiency over the past 30 or 40 years, but as we'll see with some of the effects, it's still, I think, we still have ways to go to improve some of that efficiency. Getting back to this graph, infixation, actually, so this is actually some new data we've developed using legume yields as a surrogate for infixation. And legume yields have been increasing pretty steadily, especially with soy production over the past, 50 to 60 years. And so we're seeing a continual increase in infixation for soy. And that's important. I mean, so legumes are actually quite good at so the soil nitrogen balances for legumes are actually quite good in terms of, they're usually largely in balance. But much of the nitrogen in things such as soy or alfalfa ultimately gets dispersed out to livestock, which is not quite as efficient. And so a lot of that nitrogen can enter the environment in that pathway. Again, with NOx emissions, as I mentioned, beginning with the 1990 Clean Air Act, amendments to the Clean Air Act, we've actually seen nearly a halving of the NOx emissions across the U.S., which is quite an improvement, actually a very good success story. And that's important because it's a precursor to smog and has effects on human health. Again, because natural DNF is so uncertain, we just kind of left it steady at about 4 teragrams or so coming in through background inputs. We've also mapped this out spatially. So what we've done is we've taken some spatial data sets and land cover data sets on the different types of nitrogen inputs across the U.S. We've summarized them here. We can do this anyway, any spatial scale we want. But we've done this here at the scale of 8-digit hydrologic unit codes from the USGS, which on median is about an 1,800 square kilometer watershed. And I mean, not surprisingly, the nitrogen inputs across the U.S. are concentrated in the agricultural areas, the corn, soy belt, areas in Central Valley of California that are highly intensive agricultural areas. So this is maybe not quite surprising. We can also look at recycled end inputs, and that comes from sewage, from manure inputs, and that's a little bit more distributed. Again, focused a lot on the agricultural areas, but you see places like in eastern North Carolina where the hog lots are concentrated, or in places in North Georgia with chicken feedlots, and or places out here in the Midwest where you have cattle feedlot areas. Now one thing, because we've been able to compile these data from these different sources, we've also taken kind of a stab at creating what we would call almost like a human footprint of nitrogen input across the US. And so we've taken, in this map here, what I've done is I've summed up the new nitrogen inputs at the scale of these Huckgate watersheds and divided by what we think is coming in from background sources, or at least coming in from background inputs that we think are coming in prior to European settlement, based on some larger models. And so what this does is it gives us an idea of where human modification inputs are most extreme or most intense. And again, maybe not surprisingly, you see this in the upper Midwest areas of the US and the Central Valley. But you also see places such as in eastern North Carolina, or places where you have high NOx emissions or atmospheric emissions, where that can also hop up as being a large footprint of nitrogen inputs. And because we have this nice data set available, we can also go through and code out, okay, well, in these individual watersheds, what do we think are the largest inputs of nitrogen by source to these watersheds? And so if we rank them, we can pull out those different sources and show, again, fertilizer and deposition dominate broad swaths, although in fixation, just based on magnitude alone, pops up as being important in places such as, especially in the out west, where you have a lot of alfalfa cultivation. I will mention that all these data sets, again, they're available in that publication I mentioned earlier, Frontiers, but they're also websites where they're available. We have a website for the EPA, and I can send this link around later, or if the presentation is posted, the links will be available. There's the EPA's website linking nitrogen and ecosystem services, and all data sets used in this analysis are posted there. There's also the EnviroAtlas, which is a tool for looking at ecosystem services across the US that's being developed by the EPA. It's going to be released very soon. Right now it's a beta version of the tool, but many of the data sets that I've described here are available for download. The spatial data sets are available for download from there. There's also a large number of other data sets that are very interesting and useful to look at as well. Excuse me. Getting over a cold, my daughter is brought home from daycare. So next, what I want to do is I want to take these inputs that we've developed and use that as a starting point to translate those inputs to system level losses, like land specifically to air, land, and water resources across the US. And how we did this is, it's not the easiest thing to do, but we've started off by using some simple empirical models as a way to estimate losses to the various components across the landscape, and we've actually kind of compared this with some more detailed mechanistic models, and it actually lines up pretty well, which is really nice. But I should mention this inventory effort was also, it also helped contribute to a working group on the assessment of nitrogen and interactions with climate change. And so in that working group, we were able to go through and try to evaluate the efficiency of nitrogen use across the US using these budgets and looking at different fates. And so in this process, we were able to come up with some best estimates, we think, of environmental losses going to air through oxidized N or ammonia, to different water resources, both surface water and groundwater, as well as losses to desertification, and from that also to coastal zones. So using this as a base at the national scale, and then fine-tuning it a little bit, moving it to a spatial scale based on both inputs and other considerations at the watershed scale, we've been able to kind of quantify the amount of nitrogen. Okay, so we have nitrogen coming into the US landscape, but how much of that is actually lost to the environment? And so what we've been able to do is kind of rank the losses in the environment. And these are basically the best available data sets that we have. There's no uncertainty described here, though that's on the docket for us to do at some point very soon. We think most of the nitrogen applied to the US is actually lost to surface waters, followed closely by groundwater. Much of the nitrogen also applied is volatilized and is lost in ammonia, which can be deposited elsewhere across the landscape. A fraction of the nitrogen that's applied to surface waters is lost to coastal areas. And this oxidized nitrogen, again, it's been declining, and this is actually the anthropogenic, specifically the anthropogenic component of oxidized nitrogen deposition. So it's actually a little bit smaller than we thought originally going into this analysis. And then last, we have nitrous oxide emissions, which is not surprisingly is a low fraction, but it's important because it's a very potent greenhouse gas. When we look at this across the country, again, using this empirical approach, and then fine-tuning it a little bit, and I can go into more detail with people if they're interested about that. We can look at overall loss of nitrogen to the environment. And again, we're seeing the broad swath of the Midwest, which is maybe not surprising because the inputs are kind of driving this in a large way. So we're seeing the highest losses occurring in places in southern Minnesota, Iowa, areas with intense agricultural production. We can break it apart again by where it's being lost to surface waters in particular, in this map described here. Lost to groundwater. You can see it follows very close patterns in loading the landscape, but there are some slight nuances as you kind of zoom into different watersheds. And then also lost to air, which doesn't follow agriculture as closely as the previous two maps, mainly because the losses to air are going to be concentrated more around urban areas, more industrial areas, specifically with NOx emissions. Ammonia emissions, yes, from agricultural areas, there's large losses. You can see the scales changing as well. So with these losses, we can then start to try to put some value on what these losses mean to ecosystem services or effects on human health and the environment. And how we've done this is my co-author on this, Janet Compton, in 2011 put out a paper in Letters in Ecology, kind of summarizing an approach to scale damages or benefits according to the amount of nitrogen loaded to the environment in terms of the dollars per kilogram, and $2008 or whatever was available. And so I don't expect you to see the scale here completely, but I just want to show you that we have a range, so we have about 30 or so different damages that we've quantified to various system components. And again, we can use the specific inputs to the environment or losses to the environment multiplied by these values to get an initial estimate of damages caused by nitrogen in the environment. And yes, there are many caveats with this approach, and I'm happy to discuss those. I'm sure they'll come up in the question session. But anyway, this is a start to look at damages. And so when we do this and apply this to our loss terms, what we come up with is a total annual damage cost, or at least as of 2000, of nitrogen in the environment of around $270 billion US dollars. That's about 2% of GDP. And for comparison, like net farm income in the US is something in the order of 40 to 60 billion per year. Even when you use multipliers that people in the European Union have used to try to correct that for downstream impacts of agriculture and the economy, say multiplying that by like 2 or 3, you still end up with a value less than the overall damages. And we think that the largest damages are going specifically to ecosystems, and specifically to freshwater ecosystems. I don't show this here, but I can break this out further. We also have relatively large impacts on the health and social system, and that's mainly due to effects of air pollution on human health, things like asthma or hospital visits due to respiratory distress. Those have very high costs, and so it's disproportionately large to the inputs to the environment. So the agricultural damages here, those are more like specifically to things like ozone damages to crops and things like that. So very, very small overall damages to agriculture. And we actually see, based on these numbers, a net benefit to the climate system in that although nitrous oxide is a very potent greenhouse gas, it's a very small component of the overall flux of nitrogen to the environment relative to NOx or ammonia. And those have the benefit of actually cooling the environment by creating particulates and reducing radiative forcing in the atmosphere. So we actually see a slight net benefit to the climate system. We can map this out again, and maybe not surprisingly, it follows very similarly to agricultural nitrogen loading. But the scale here, what I want to point out is, in some of these areas, we're calculating damages in terms of a per hectare scale of up to $3,000, the really high end of damages to the landscape. And these are damages based on where the nitrogen is entering the environment. So some of these damages might be felt, say, in the Gulf of Mexico or elsewhere where the nitrogen moves in the landscape, but we're attributing it to where the nitrogen is entering the landscape or entering the environment. Again, areas such as the upper Midwest, the Central Valley, California, and places along the East Coast kind of pop up. And we can again break this apart by freshwater, different types of damages. And I mean, for the freshwater, because this is a water science seminar, I'm going to highlight some of the water damages. Freshwater damage costs actually amount to be the largest based on our numbers, upwards of almost $2,000 per hectare per year. So on the median damage at the Huck 8 scale that I'm showing here is something on the order of $200 per hectare per year in damages of nitrogen. I think the median net farm income across the U.S. is something on the order of $20 to $25 per hectare per year at the scale of Huck 8s, if you do sum it up like that. We can do this by drinking water as well. Again, assuming that the nitrogen delivered to groundwater is going to impact human health. And this contracts with nitrogen loads across the U.S. But areas that actually have documented groundwater problems show up here. Places like well, I think the aquifer in Nebraska, that's a kind of it's almost a poster child for issues with nitrogen pollution across the U.S. Same thing with the Snake River Valley in Idaho or in the Central Valley of California as well. The air pollution costs show a different pattern. Again, it's more concentrated around urban or industrial centers where people live, where they're exposed to air pollution. And so those costs can range up to $300 per hectare per year. And actually, an analysis of the Chesapeake Bay, which I cite, we use some of the data here, although nitrogen loads to the agricultural systems are higher overall, they actually estimate that damages to human health from air pollution exceed inputs to aquatic systems. But they're actually using a little older data. But anyway, so we can also compare this with the distribution of net farm income across the U.S., just as kind of a face value comparison of the damages versus one way of measuring the benefit of nitrogen. It's not inclusive because there are many other aspects of nitrogen that are very important. Again, the value of food to someone who's hungry, that's infinite. So that's one of the issues of trying to do these types of comparisons in a cost-benefit analysis. But we at least want to start the conversation by putting some of these numbers out here for discussion. So I had 3 parts, but I also want to end with kind of a part 4 here. I'm probably way ahead of schedule here, but that's how I talk, I guess. Part 4, what can we do or what can you do? And so I'm also become involved with an effort to do more of a comprehensive life cycle assessment of nitrogen in the U.S. And so looking at different economic and social drivers that drive nitrogen use or nitrogen decisions. And I want to end with just some summary of what we do both at the government scale and also what you can do to look at your own nitrogen, ultimately your nitrogen footprint on the environment. And so what I'm going to start off with is, I've emphasized that nitrogen has many different forms and many different inputs. And so you can see a figure like this is really complex. This is actually the nitrogen cascade that Jim Galloway developed about a decade ago. And you can see very different forms of nitrogen, very different impacts. And so we have different mechanisms, both regulatory and voluntary or incentive-based approaches to try to address issues with nitrogen pollution in the U.S. For example, we have the Clean Air Act, originally passed in 1970 with the amendments in 1990, that have the intent of trying to improve air quality and reduce air pollution. And we've actually seen, again, a very significant decline, again, more than a halving since about 1990 in NOx emissions. So that, I would qualify that as a success story. I will mention, however, that EPA does not regulate ammonia, which can be also quite important for emissions in many areas that we measure. We also have things in place, at least at the federal level to try to reduce or improve water quality associated with nitrogen pollution. We have the Clean Water Act in 1972, and also the Coastal Zone Management Act that have mechanisms in place to try to reduce nutrient loading and nitrogen pollution. Both working at the federal level and more specifically working with states in order to set criteria for nitrogen levels and nutrient levels. But even with the passage of the Clean Water Act and the directive to develop criteria, currently only about half the states in the U.S., and we can see that Nebraska is one of them, actually have criteria for nitrogen or more broadly phosphorus criteria for surface waters across the U.S. And kind of compare this with There was a recent report, a recent survey conducted by the EPA, the National Rivers and Streams Assessment across the U.S., and they've estimated that about, I think it's about a little less than half of the streams and rivers in the U.S. are in fair or poor condition because of high levels of nitrogen. And so it's kind of a mixed story, a mixed bag in terms of the success of things like the Clean Water Act across the U.S. There have been local success stories, like Tampa Bay, for example, has greatly been able to reduce their nitrogen loads to Tampa Bay, and this has greatly improved the seagrass beds, in particular for fisheries production. We also have the Safe Water Drinking Act that has been put in place, mainly looking at the EPA's got a maximum contaminant level for nitrate and groundwater of 10 milligrams per liter of nitrate and nitrogen that's been set, and so we have mechanisms in place to try to improve water quality. Actually, there's one, I think, in Nebraska trying to improve water quality in groundwater in the Central Platte River, and it's had some degree of success actually reducing nitrate concentrations. But if you look nationally, you can see that the number of nitrate violations in drinking water exceeding the maximum contaminant level has been steadily increasing for the past, well, since it's been measured since the mid-1990s. And so it begs the question of whether this is actually because of increased nitrogen loading, or are we just starting to look more for nitrate violations in groundwater? So right now we're still seeing over 1,000 violations. We also have things in place such as the Conservation Reserve Program, which it's not regulatory, it's more of a voluntary or incentive-based program, which many of you probably are familiar with. That's put in place to try to set aside lands to, on the landscape to either restore or maintain ecological function. And I will say though that, with the provision of the Farm Bill, the past few Farm Bills, the lands that go into the CRP, the cap on that is steadily decreasing. Although there are some different practices that are being implemented that could be beneficial for nitrogen management, things like riparian buffers that can help reduce nitrogen runoff from the landscape. So again, I would say that right now, in terms of regulation or programs to try to reduce nitrogen or improve nitrogen use efficiency across the U.S., there's a mixed bag of either successes, I would say failures, but the challenges that still exist. But I also want to point out that there's much that you can do at the personal level to try to improve your nitrogen use efficiency or footprint. And what I have here is a link to an EPA webpage that details some actions that you can take to try to help reduce your nitrogen footprint. And I also want to direct you to a tool that some colleagues at the University of Virginia has developed, Ali mentioned Galloway, where you can go and actually go through a calculator and calculate your nitrogen footprint from your daily actions. And you can see where your nitrogen use is most intense, and potentially you might be able to take actions to try to reduce that. It's very similar to carbon footprint calculator. So with that, by the way, I have to schedule, but I do want to acknowledge funding sources. Again, I had the opportunity to work with the EPA, ORISE, for the past 4 years, and the National Research Council as well, part of the EPA, and a number of individuals have helped out with this for talking about ways to move forward with the analysis and interpret these data. And with that, I think I can, so I have the links on this presentation that should be available for those who are interested in finding out more.
Plenty of time for questions and lots of hands right away. Let's start with that.
I really enjoyed your presentation. I'm Patricia Gassini from the Department of Agronomy. Sorry, I got that code too. And I really like your inventory part of the story, in which, I think that you did a really good job there, and I really like to see those error bars indicating the uncertainty. Yeah. But then when you try to translate inputs of nitrogen into impact, then the thing started getting a little bit more unclear to me. It seems like you use some sort of fixed percentages to assign some nitrogen losses based on nitrogen inputs. And then on your last figures, I didn't see any measure of uncertainty. Yeah, there were some just fixed values. So I just wonder, if we're really looking at this, in the right way, in the sense that And we are using some fixed percentages values to estimate losses based probably on some very old work, which really look at nitrogen inputs and doesn't look at nitrogen surplus from the system, which probably is a more strong proxy for nitrogen impact than nitrogen inputs.
Yeah.
But having said that, I mean, if you just change those percentages by 5%, then your final value is going to change so much, So I mean, I just want to hear your reaction about that part of the story.
That's completely fair criticism. We have not had a chance to do that yet, but I fully acknowledge that. So the modeling there, I think we're probably going to be working toward to improve that, use more spatially explicit approaches to do that. At loss, but I want to point out that if you look at some models like Sparrow from the USGS, our numbers that we calculate actually compare very favorably to what they've calculated. Now, in terms of the error aspect, yes, that's a huge issue, and I think that's something that we're going to have to do before we can actually get this published in the peer-reviewed literature. But I think that at least as a starting point to get the conversation going about what this might mean for losses and ultimately dollar amounts, I think it's a good way to start thinking about the analysis. But I fully acknowledge that needs to happen in the future.
Great.
I'm probably not satisfied, but I can talk to you afterwards about it.
About, was a chart you had about 6 or 7 slides back on the nitrogen pollution escalation?
The incidences?
Yes. That one. I'm curious about that sudden drop out of 2000, 2001. What accounts for that?
I don't know enough about the data set to comment on that, so I can't.
Can you conjecture?
Well, let's see.
This is just conjecture, but
Yeah.
there was a pretty massive sort of drought at that time, in which case if you look at the 2003 rains and floods that we had that really contributed to the Gulf of Mexico, essentially we flushed a lot of that resident nitrogen at that
Yeah.
time. So that's just a conjecture. Because essentially I know here in the Great Plains we were coming out of our 10, 11-year drought cycle about 93 when I put my experiments in for drought and it got flooded.
Yeah, well, that's great to know. Again, I pulled this from the website. I can't comment on specific years and why those patterns might be apparent.
I first want to comment, you got your PhD at an excellent university.
Oh, thank you. Yeah.
And that,
Yeah. Enjoy OSU.
we won't talk about Virginia Tech.
Oh.
But with regards to what's happening, and you have like circa 2000, I think we've gone through such a land use change since 2007 with biofuels coming on, particularly within the Great Plains and Midwest. And you top that off with the increased climate change that's occurring, so that you're now looking at South Dakota, even North Dakota being tile drained, as well as the erratic weather events that occurred in 2012 and 2013, where essentially you now have a drought situation where you get high amounts of nitrogen going there and then flooding off in the subsequent years. With all that, you then showed the map of the benefits of nitrogen, saying, look at these profits that are occurring. Now I know with the profits, essentially farmers add what we call hedge your bets, increase in fertilizers. So you have several things happening here where these could just like overwhelm some of the other activities you're trying to do. You're trying to decrease nitrogen by this much here, yet we're talking about a land use change that is probably greater than when the soybeans came out, which is greater than when tractors were invented. And so I think the whole paradigm in programs is going to have to radically change.
I completely agree with that. And again, it's because there have been lags in terms of when these types of data sets become available for these types of analyses. That's why we have included more recent information, again, with biofuel switches or things like that. So I completely agree that you have to think about those types of interacting things that are occurring at the social or economic level, and then trying to how that cascades out to the environment and can affect nitrogen losses and impacts in the environment. I think that's a huge area of research that we're trying to tackle with that life cycle approach, using more recent data.
All of the data that you summarized in the maps was circa 2000, and as we all know, a lot of things have happened since 2000. I mean, there's been major conservation management programs implemented. And so I'm wondering if, are you in the process of putting together similar maps for, let's say, 2010? Or, because that, I think that's what we really need to see, because the question is, you know, it's nice to describe the problem, but, you know, nothing that was presented surprised me in any way, or anything really new. I mean, it was a nice, concise presentation. But what I want to know is, you know, have the things that we've been doing had an impact, or had a positive impact in terms of reducing, you know, these nitrogen, negative nitrogen impacts?
So I will notice, I will mention the National Rivers and Stream Assessment that I mentioned. So the most recent surveys that have been published from 2007, 45% of the streams across the U.S. are in very poor condition to total nitrogen. If you look at the 2002 or 1997, it's more like 55 or 60% are in fair or poor condition due to elevated nitrogen concentration. So there has been a decline, at least in terms of stream or river, at least in terms of the at the scale of the synoptic sampling from the EPA. So there is some indication that things are getting a little bit better. In terms of data available, so the EnviroAtlas will have more recent data, more on 2006, 2007 data sets on nitrogen inputs to the U.S. A lot of it, there are lags associated with some of these data that come available for the analysis. So that's one of the reasons why we're constrained by 2000.
Sure.
But there is some evidence that things are improving in some areas.
Because we need, you know, we need something to gauge, because, you know, I'm looking for solutions to problems.
Yes.
And so are the things we're doing moving us in the right direction, or are they moving us in the wrong direction?
Yeah.
I mean,
a lot of it's due to data availability as well. Some of this stuff, I mean, you want to know answers to these questions, but at the scale that it needs to be made available, it may not exist, or there's not enough time series to really evaluate trends like that.
Okay.
Yeah, I have another one. And following up on that, yeah, the question is, what's the benchmark to say, you know, now we are better or worse? And I wonder, I mean, if you can create a graph like the one that you show on one of your first slides in which you were showing the nitrogen inputs over time. It would be nice to also see that the same slide, but having a nitrogen output or nitrogen impact or nitrogen loss as a dependent variable there.
Okay.
Because my feeling is that if you look at I mean, how we are doing now compared with 30 years ago, I think we are in a much better position now.
Oh.
And because, for example, I mean, in the case of Nebraska, Iowa, Illinois, the three major producing states of corn in the United States, the nitrogen rate hasn't increased in the last 30 years, while total production has increased substantially.
Yes, yeah.
So in terms of efficiency, we are doing like better over time. So when you get to the slide in which you ask, what can we do? I mean, do we need to change what we have been doing during the last 30 years, or do we need to come up with something new?
Well, so again, I mentioned at the beginning, we have done a lot to improve our nitrogen use efficiency, like I mentioned, in the past 30 years. But I think there are ways to do better. There's a recent report that was put out by the Science Advisory Board to the US EPA that summarizes a lot of these potential ways to even improve nitrogen use efficiency even more, using technology and practices that are available now without development of new technology. Things like improved application of nitrogen fertilizer, timing and space on the landscape that can be implemented now that just aren't being implemented. So I would encourage you to look at that report for one, and I can forward links onto that. But so that is a good recommendation for looking for that type of figure, though, for future presentations.
Yeah, I think there is one important component that they maybe want to elaborate a little bit is the transport in the atmosphere, the atmospheric transport.
Yes.
I mean, once the, let's say, NOx or ammonia are emitted into the atmosphere, they're being transported.
Yeah.
NOx might have a lifetime of one day in average, and so we, like in Nebraska, we got pollutants from Kansas in one day. You see that. On the other hand, when the NOx becomes the pain in the atmosphere, they can stay for months.
Yeah.
I mean, in colder temperature. So it's basically considering the Asian, there is rising emissions of NOx. They can actually carry all over as a pain, get to the across the Pacific Ocean, deposit it in the western part of the U.S., and all of a sudden become NOx, and you see the ozone formation over there. So I think if we want to consider the cost and benefits, the air quality and how they transport and affect each other. Even among the US, how do we affect each other? That's probably also an important factor.
It is a very important factor. There's some recent work actually that have come out to look at those kind of international trade effects. A recent paper in ES&T that have looked at ammonia emissions and transport. But I would agree. I can't speak to that because that's enough. It was a good point that I would like to raise.
We have one more here?
Something related to the two questions that were brought up, the Clean Water Assessment Program, the QUAC report. Essentially looked at watersheds that had had best management practices put in up to 15 years, and the endpoints either didn't change or got worse. But the question became is if they hadn't put in the BMPs, would be a lot more worse. So the metric we sort of talked about, well, we are less worse than we could have been. And that gets to how can we then measure these, Pat, because land use changes faster than even endpoints given some of the geologic movement of some of these pollutants. So we need to recognize that. But the thing that Pat brought up is with your maps and with the streams, I would think you would be able to mine that data to see where you have gotten success and try to correlate that to what caused that success. And maybe look at those areas where you actually didn't get, it was much, much more worser, and correlate it to that and not deal with anything in the extreme that would be confounding. Look for those, big drivers.
There are postdocs that are coming on in EPA that are going to be looking at that pattern in the coming years. So that is on the docket, and that's some of the research ideas that are going to be taken forward with that data set. I will mention that. These are publicly available data sets, so if people are interested in looking at them on their own, they're freely available to look at as well. I think that's a good point to try to pull out and look at time courses for repeated samples, repeated areas.
Is it a regional thing? Is it a human dimensions thing? Is it a hydrologic thing?
That's a good point. I mean, because again, the residence times of, say, nitrate and groundwater, if it's on the order scale of decades or centuries, any actions you have now are not going to be realized in any real political cycle or short-term period, but for the long-term benefit, it's worth doing still to try to get below levels, or even if you're going to not realize that for 3 or 4 decades, which is what they've seen in England actually in more studies that have done this.
Yeah.
Great. All right, well, thanks, everybody. I wanted to thank Dan with one more thing, because we love nitrogen so much. I found the mug with as many ends on it as I possibly could. So thank you for coming and visiting.
Great. Thank you.